Ladies and gentlemen, boys and girls, thank you very much. It was a lovely 6-hour drive from Sydney. I believe some of you came from Amsterdam, so probably the same length of time. Okay, so let's begin. Just quickly on the Cusco problem, just quickly, I mean, none of this is my research, of course, like most things in life. It's more evident in, say, galaxies that aren't of the large kind, so they don't possess a supermassive black hole, and with n-body simulations under lambda cold dark matter, you would expect to see much more of a higher density profile of black hole in the center, but we don't actually see that. We as in humans, not me personally. And so for that reason, dark matter has to have some other property, some sort of limited self-interacting property. And so there's a few things that are being conjectured at the moment, and I would say I was just going to add that to what you're going to say about the properties of QDM being having some extra interaction. So what I wanted to do was I spent the last year taking the mathematics of Dr. Ernest's work, and I just wanted to give you an example of, and I'm going to speak in layman's terms, so please forgive me anybody who is way ahead of what I'm saying, but I'm speaking at this rate for everybody, why not? So I just got here the classical description of the nucleus with the electron, and you can imagine instead of that, just by analogizing the mathematics of the Schrodinger equation, you can move that into, say, something analogous to a galaxy with a particle orbiting in a quantum mechanic fashion. The difference would be, of course, that that type of extreme Rydberg state would have an energy level of about 10 to the 34, or let's just say, I think, correct me if I'm wrong, but 10 billion trillion times the order of the energy level you expect to see in a standard particle. And I'm going to refer to this quite a fair bit. What we have here is, if you can imagine something in a ground state, let's just say a hydrogen atom in a ground state, you would have the energy level of 1, and the orbit type would be 0, which is the max orbit. The orbital would be n-1, and 1 minus 1 is 0, so that's the only movement that you could have in terms of a transition, because there's that ground state. If it was at the second energy level, which would be out here, for example, then you could say n would equal 2, n minus 1 would be 1, so then that would be the ground state. But now you can have two orbital types. You could have the max orbital of 1, max orbital of 2, so you can occupy this state and also this state. And of course, the more energy levels that you, let's just call it analogously, inject into this particle and swell it up, you have, of course, proportionally an increasingly number of orbitals that you can occupy, or that the position can occupy. And that then means that there are so many orbital types existing in the hypothetical extreme Rydberg state of this quantum dark matter particle, that it becomes very difficult to then imagine, well, which ones are we looking for exactly? And one of the beauties of running the mathematics is that it actually reduces the potential possibility down to ones with extremely high orbital numbers with respect to their energy levels. And that constant, which is n minus L, which would give you a very low p-value, and that's the p-value that Dr. Ernest has defined here as p being n minus L. And the reason it works out to be a diagonal for each specific p is because on this diagonal, what you would have is the orbital being the maximum orbital for any given n. So if n was a value of 1,000,000, then the L value would be 1,000,000 minus 1. And if the n value was 1,000,000,000, it would be 1,000,000,000 minus 1. So they would all occupy that p state, and that's what they would have in common. And there's a reason for that, but this is for all of you mathematicians out there, probably being all of you. This is the Schrodinger equation, which, of course, I'm not sure if people are familiar with it. You probably are backwards and forwards. I'm not sure of everyone's credentials. And what Dr. Ernest has done is simply creating an analogous equation for quantum dark matter, and by simply swapping, for example, A naught with B naught, and A naught was to do with the Bohr radius, which is the ground state in a hydrogen atom with respect to electrons, or the electron radius ground state, so that's the radius. And by swapping that with B naught, then we simply get, as we were saying previously, you can just get, instead of this radius being the radius of a hydrogen atom, you could say that that's the radius in terms of the galaxy out to the quantum particle that's in a dark matter state. Now, it would have been great to run mathematical simulations up to energy levels of 10 to the 34. That would be beautiful. But of course, those computers don't exist, at least in my house. It would be nice. But because they don't, then, as you all probably guessed, I was looking for other methods that were as independent as possible to try and arrive to a converging trend. And that trend would be that as we increase energy levels, or whether we increased delta P's in a negative direction, or if we looked at specific orbital transitions of +1 or -1, which I'll talk about in a sec, whether we start to see that the properties of these particles get closer and closer to what we're looking for dark matter particles themselves. And so what I actually did was, I'm just going to show you a very, very small fraction of what I was spending time on last year. And it was a year without video games, of course. That was fun. All right, so what we have here is, I've controlled here for, what we've got, delta P is -3 and delta P is -3 here. And just to show you roughly what that means, is that if you look here, we have P equals 4. So on this particular line, what we have for any given energy level of this hypothetical quantum dark matter extreme Rydberg state, we would these have in common that the orbital is the energy level of that specific particle -4, and they will all be on the P equals 4. Now a transition in terms of decay down to, let's say, what do we got here, down to P equals 1, there's two possible ways you can go, because you can go for delta L being -1, which would be to the right, then D would transition to A, and for delta L being +1, it would transition to what I've called here C prime, and the C prime is invisible, just like dark matter. And so there is the energy level drop here is actually just 2 levels down, whereas here it's 4 levels down, and yet they both fall on the P equals 1 line. So that there is a delta P transition from 4 to 1, which is -3. And that's what I have here. So I've controlled it at -3. And the difference, I've kept the energy levels the same from 10 to 100, or 5 to 100. There's a reason for that there is no 5 on where delta L is -1. And I've just controlled for delta L. So with here, delta L is -1, delta L is +1. We can see that if you keep everything else, the other parameters the same, that the decay rate of this hypothetical particle actually decreases dramatically. We can see here that with delta L is -1, we have a decay rate of something in order of, say, 100 per second, or the order of 10 to 2 per second. Here, it drops dramatically. We can see here that it's sort of a 0.1 or a 0.01. So that shows us that there is much more of a chance that if we're going to look for these particles, we would expect that we would want them to have a transition of delta L as +1, or at least there'd be more of those, or more of a chance of finding ones that have those properties, because of the fact that they naturally have less of a decay rate per second, which means that they would exist for a longer period. And the reason for that, of course, is because dark matter still exists today. So if it was decaying anything faster than 10 to the 17 seconds, it shouldn't still be in existence today, being the age of the universe. So we at least want to see it lasting for that long. The next thing I did, do we have much time left? Am I out? 5 minutes, all right. So the next thing I did was actually now keep it at delta L as -1 and show us the transition of delta P. So this is delta P -3 for the same energy levels, and delta P was -10. And you can tell already, of course, that the decay rate actually drops. So we can see that there is a lower decay rate when we look at the delta P transition for -10 as compared to -3. And I've just got that graph to remind us again, to move 10, you'd have to have P equals 11, so something up here, and that sort of transition up there from, let's call it G, for example, something like that. I might not get through this all, but that's all right. Now this one here was analogous to the last one, almost identical, except what I was actually showing here, which was delta L -1, that was what I was controlling for. I now here swap that to delta L as +1. And not only is the decay rate much less as compared to its delta L negative 1 sibling, it's significantly less as compared to what it is for when I'm looking at delta P equals negative 3 compared to delta P is negative 10. So what do I mean? I mean here the decay rate at negative 3 is about, let's just say, 0.01 in terms of order of magnitude, where here it becomes 1 in 10,000. So instead of 1 in 100, we're looking at 1 in 10,000. And that's a significant drop. So whatever the group is of these specific particles, 1 in 10,000 decaying per second, if you imagine a rough analogy. Whereas if you notice back here, what I was showing before, the magnification of this reduction in decay rate is not as significant when we're looking at the same comparative transition, delta P negative 3, delta P is negative 10, but with delta L is negative 1, we can see that the drop is not as much. So it does seem thus far that if we were to raise the energy level from, let's say, N100 up to, let's say, 10 million, if anyone has access to a supercomputer one day, then that trend would likely continue thus far, of course, without getting into the rest of the information. What I wanted to show here was negative 10 on its own, but the energy level had now increased from 120 to 200. Now, each one of these calculations, I actually ran this, it took a few hours on Mathematica. I actually ran one of these on Excel, and it took a week. And that was just on Excel without even doing it by hand. So the type of calculations were insane, and it's because of the exponential increase of potential decay channels that are available to a particle with higher energy levels that you probably know about. And this here, as you can see again, we're now looking at, this is for delta L plus 1 again, so we can see that having the property of delta L plus 1 seems to be the winner. And just by going up from 100 to 200, we can see that the decay rate goes from, instead of 1 in 10,000, it's now 1 in 10 billion. And so it's an enormous increase in longevity of these type of particles that we're looking for. And it doesn't seem that it's slowing down, it seems as though it's speeding up. So the other calculation that I was running was looking at the state lifetimes, which was adding up all of the decay channels, which you can ask the doc about, and seeing the potential lifetime of certain particles that had the high orbital number, in other words, a low p-value, and the high n value. And this one here was where n went from 20 up to 200. And this is the part that's fascinating. You can see that they last almost nothing down here. So that these type of, what do you call it, particles with these properties, being the low energy level, for example, would not be a suitable candidate, but that would be self-evident, I'm guessing, because they would pretty much be baryonic. But if we move up to 200, you can see that instead of it lasting for an instant, it now lasts for an instant and a little bit more of an instant. So 0.0003 is how many seconds that particle would survive at an energy level of n equals 200, which of course is unbelievably low in comparison to what we're looking for. But what I did here was, the top one there is 200. Here, it's 500. Now, 500 is only 2.5 times more than 200, and yet, instead of 0.003, it's now 0.05, or 0.035, sorry. So we've gone orders of magnitude upwards in terms of its potential state lifetime, theoretically. It'd be good if we could observe these things. All right, so the last thing I wanted to do was have a look at fixing the energy level, and then having a look at the variations if in orbital type as we move across from high orbital or max orbitals down to the minimum orbital, or low p to max p. And what you can see is, well, of course, once again, this is where the delta L is +1, this is delta L -1. And you can see the significant difference. We're looking here at about somewhere around 0 or a bit less than 0. Here we've got here, this is 10 to the -15, which is, as you can tell, that's almost nothing in terms of a decay rate as compared to the decay rates above. But here's the interesting thing. The interesting thing, well, for me anyway, and for Professor Alanonis, was that, or is that, as you move outwards, right, with the p-value, you notice that the effect of the longevity with increasing energy levels, okay, with these energy levels here, because what I've got here is these are the delta p's, so I'm controlling to look at all the different delta p's. I've kept the energy level the same. but the delta P is significantly affected only for max orbital type of structures. Whereas if we look at high NPs, none of them are actually really affected at all. So we're narrowing down significantly what we would want to look for with such a hypothetical particle. The last thing I noticed, how long do I have? Another minute or two?
Still 5 minutes.
5 minutes, that's great. Time has stood still for me, thank you. So what I then noticed after running all of that was that by looking at the same energy levels and the same orbital structure, orbital transition of delta L, these here are the negative ones. What I noticed is that as you increase delta P, there seemed to be a shift downwards in the graph. And that shift downwards is blurry at the low delta P, but at high delta P it started to actually become very clear. And it seemed as though the graph is shifting downwards as we increased delta P. And I wanted to know if that was just some sort of illusion, or if it was not, how accurate was this, and was it exponentially decreasing, increasing, etc. What I noticed was I compared one particular point being just, let's say, P equals, P equals 1, P equals 1, where L is the max orbital, and on every single one. And I just checked how much was how the overlap was, sort of like if you get pixels on a photo, and you want to imagine what are we shifting down by if the photo is getting warped or stretched or something like that. And what I did notice is that there is a relationship between the increase in delta P in a negative direction, and the multiplicative factor is still positive this whole time. So it is moving downwards on this side, as far as this can tell us on this P1, but it's moving down at a slower and slower factor, or a smaller factor. So it looks like the delta P transition has less of an effect on pushing these particles into potentially what we want to look for with dark matter, as compared to raising the energy level. Okay, and the reason I wanted to do that was so that we weren't guessing whether it was delta P or the energy level that had more of an effect. The next thing that I noticed was then, I did this one, this is our last graph, but I actually took each point along all of these deltas, and I got an average, and then I took the average of every single point and compared the averages. And the reason I did that was to actually find out two things. One was that I noticed that there was a decrease as P increased, and that decrease shows us that the graph is not shifting downwards, it's actually rotating. If that's like a hinge, that's sort of being dragged downwards, sort of like if I held my face here and pulled the left side down. So I'm getting this funhouse mirror stretch, which shows us that the magnification of the properties that we want to see, hopefully, or the direction in which we want to move towards to see those particles, is happening specifically at this section. So we're looking for that specific type, which is really good because it helps us eliminate all the other possibilities and shows a very strong trend into what we're looking for. Then I also noticed, of course, that as the points moved across, the actual error decreased. And that shows that it was much more confident in the overlap as we moved closer and closer towards this side here, which is consistent with that hinge sort of rotation that we're expecting to see. There's sort of a translation downwards, but the downward translation has less of an impact as we move across. Okay. And this black screen is to represent dark matter. So thank you very much. It was lovely to talk to you.
Here we go.